video. I'm making 3 videos today. This will be fun. So relationship number 4. Okay, this is the one that we want to talk about right now. What happened with relationship number 4, or station number 4? Do you remember? Okay, so the can had some boiling water in it, just a little bit at the very bottom. Okay, you flip that over into the ice water bath, and it crushes. Okay, it immediately crushes. So the questions we have here. So that's your observation. Hopefully you already have that written down. This is kind of a tough one to explain. Okay, so I want to help you out with this. Why do you think this happened to the can? So give me some ideas here. Why did this happen?
The temperature inside the can is higher than outside, which made the pressure inside the can higher.
Okay.
So it makes it push out. And with the ice, the rapid decrease of the pressure made the air from the outside crush it.
Okay. All right. So you're on the right track there. And so what was basically said, just for the people who are watching the video, because you didn't hear that, is that the pressure on the inside of the can increased, so it was pushing out against the can. Okay. Then when you flipped it upside down, the gas cooled very quickly. Okay. And so then the pressure decreased, and then so you got all that pressure on the outside that basically crushed it. Okay. So you're definitely on the right track there. There's a couple of things that are happening in this one, and this is why this one's related to the combined gas law. Okay. One of the things that is happening when a gas gets heated up, when we heat up a gas, what happens to its volume? It increases, right? I mean, remember the balloon thing that we talked about the other day, right? When you heat up the balloon, its volume increases, okay? So we were heating up that can. There's just a little bit of water in the can, so the rest of that can is filled with gas. Can we agree with that? Okay? So when you heat up that can, the gas inside the can starts to heat up, and the volume increases. Now, what happens if the volume in that can increases? Can the can expand like the balloon can?
No.
No. So all the gas goes where? It goes out of the out of the can. Okay? It leaves because it has nowhere else to go. So it goes out through the hole in the top of the can. All right? So what you've done, essentially, using Charles' law, we have heated up the gas, and now the volume's expanded so that there's a lot less gas in there than there was. Does that make sense? Now, if there's a lot less gas in there, why isn't the can imploding when you're heating it up? Okay, the gas particles that are in there, they're moving really fast, and they're hitting the side of that can, and they're keeping it from imploding, right? Okay, you guys, do you understand that, like, if we didn't have external or internal pressure pushing out on our bodies right now, that we would all crush from the air pressure around us, okay? The air pressure around us, and I need to find this video. Ernst was telling me about it the other day. It's enough to crush a railway car if you suck all the pressure out of it, okay? I mean, there's a lot of, it's enough to crush one of his monster cans. He commonly does that as a demo where he'll, and they make a really loud noise. Those monster cans are pretty well built, okay? But yeah, air pressure is pretty intense. We just don't feel the effects of it because we have the same pressure inside and outside our bodies. Our pressure is usually equalized, okay? But if you've got a can like that, okay, and the pressure is equalized while you're heating it because the gas particles that are still in the can are pushing out against the can just as much as the air pressure is pushing in on it, okay? But when we flip that can over, we did 2 things, okay? What's the first thing that we did when we flipped the can over? What do we do to the gas inside the can? Okay, well, for one thing, we trapped it, right? Okay? So that gas can't get away now because we took away the only spot, or new gas can't get in either, okay? Because we took away the only spot where gas could get in or out. What's the other thing we did to the gas? Put it in an ice bath, so what were we doing to it? We're cooling down the gas, right? Okay, so now we've got a gas in there. There's not very much gas, right? Because most of the gas left while we were heating it. And we are cooling down the gas very, very rapidly. So what does all that gas do? Well, no, it can't go anywhere. It slows down, and so now it's not pushing against the sides of the container nearly as hard, right? Does that make sense? So now it can't compete with air pressure on the outside, okay? So then the air pressure on the outside just crushes it. okay? Because there's just a little bit of gas. It's not a fair fight anymore. There's just a tiny bit of gas inside the can, and it's moving very slowly, and so the air pressure around it just completely crushes it. Does that make sense? Okay? So there's two things going on, and those two things are, and I meant to talk about this before we went over the combined gas law, but I was trying to get through the notes yesterday and still failed. But the question here, does this change your ideas on the relationship between gas pressure, gas volume, and gas temperature? My guess is no, because we've already talked about those things, right? But what is the relationship between temperature and pressure? We just talked about it. This is the important part. The relationship between temperature and pressure. Try the other one. The other direction. If the temperature goes up, what's going to happen to the pressure? The pressure is going to go up, right? Okay? This is why you don't throw an aerosol can into a fire. It's a really bad idea, okay? Those aerosol cans are they already have a lot of pressurized air inside of there, okay? If you throw that into a fire, now you have greatly increased the pressure inside that can, and guess what could happen to that can? It could explode, and if a metal can explodes, that's a bad thing because now you've got shrapnel flying, okay? And that could really hurt you, okay? So do not throw an aerosol can into a fire, okay? That's just a very bad idea. But the reason why is because when you increase the temperature, you increase the pressure, okay? The relationship between temperature and volume. We know that one because we already did it, right? Increase the temperature, what do you do to the volume? The volume increases as well, all right? So what that would have led us to if we had done this first was something like the combined gas law, where you put, you've got your P1 V1 over T1 equals P2 V2 over T2. Okay? Does that make sense for the can? All right, so that's it for that one. We're going to talk about station number 1 probably on Monday because I want to get through the ideal gas law stuff today so that you can do some practice problems on that. So we'll talk about Graham's law of effusion on Monday and then go over that last part of the lab. So the lab will not need to be turned in until probably Tuesday. Or maybe I'll just have you turn it in Monday since we're talking about it in class. Yeah, it is kind of nice to not have to put them in the lab notebook every once in a while. It's kind of nice to not have to grade those lab notebooks every once in a while, too. All right, so that's it for station number 4.